All right, let's go ahead and start our next unit on acids and bases. So we did a little intro of acids and bases several units ago. Now we're going to do some more calculations, especially with acids and bases. So all of the solutions that we will be dealing with in this unit are aqueous solutions. So you have some substance dissolved in water. And now the strong acids and strong bases, remember we said that they're called strong because they are strong electrolytes. And this has significance when we do calculations involving acids and bases. Strong electrolytes because they ionize in the case of an acid or dissociate in the case of a base completely. So that term ionize means to form ions. So applies to either acids or bases. So just understand that strong acids and strong bases completely break apart into ions, making their solutions excellent conductors of electricity. That's why they are called strong. Consequently, ion concentration then can be calculated directly from the molarity or concentration of the strong electrolyte. So we've done this before where we've calculated concentrations of ions in solution. Pretty easy to do that for strong acids and strong bases. As we'll see, not so easy with weak acids and weak bases. So that's why it's important to memorize all of these strong acids and strong bases. So when you encounter a calculation, you'll know if it is going to be easy, if it's strong, or if it's going to be difficult, as we'll see in our next lesson. So let's take a look at what I'm talking about here. Go to example 18.1 on page 703 and read along with me. It says calculate the concentration of Ba plus 2 and OH minus ions in 0.030 molar barium hydroxide. So let me just walk you through it and set it up for you. So I always want to start off with the balanced dissociation equation or balanced ionization equation. So we're going to call it a dissociation equation since this is an ionic solid. Important thing here is for any strong acid, strong base, we put a one-way arrow saying that all of that substance breaks apart into ions. Now again, make sure your equation is balanced, especially important with these calculations. And so what we're given is the concentration of the solution as a whole. So the barium hydroxide solution has a concentration of 0.030, and we're asked to determine the concentrations of the ions in the solution. Now in the book, it kind of does a SCAR type table thing. You don't need to do that. In fact, I'd rather you set it up this way. So take our concentration of the solution as a whole, and then we're going to use a conversion factor based on our balanced dissociation equation to get the concentration of each of the ions in solution. So it's technically 1 mole of barium ions for 1 mole of barium hydroxide. So for every 1 mole of barium hydroxide that dissolves, you produce 1 mole of barium ions. Therefore, the concentration of the barium ions in solution is 0.030. Now, the only difference for hydroxide, again, same setup, I'm just going to shorten it up. You don't want to take the shortcut, so show the whole work, is we have 2 moles of hydroxide ions for every 1 mole of barium hydroxide. This is true for all of the strong bases that are group 2 hydroxides. And so we get, again, very, very important, as we'll see in a little bit when we start doing calculations of pH, that you know the concentration of hydroxide ions in this solution. So that's what that is. All right, turn to page 736. Let's do exercise number 7, and let's go ahead and do all 3 of those. So A, B, and C get the concentration of the constituent ions in solution. We're going to leave out a couple. I'll explain that later, so just do what we did in this last example problem. Go ahead and pause the video and set those up now, please. So here are our results. Concentration of, well, let's go to letter A. Strontium hydroxide is a strong base. So it completely dissociates into 1 mole of strontium ions and 2 moles of hydroxide ions. So we get 0.0105 molar for the strontium, 0.0210 molar for the hydroxide. Make sure to include units with your answer, even though we put the formulas in brackets. HClO3, that is called chloric acid. Chloric acid is a strong acid, so it completely ionizes, produces 1 mole of hydrogen ions and 1 mole of chlorate ions per mole of the acid that ionizes, and so their concentrations in solution will be 0.0105 molar for each. And then letter C, this is neither an acid nor a base. This is a soluble salt. All soluble salts are like strong acids and strong bases, strong electrolytes. So it dissociates completely into 2 moles of potassium ions and 1 mole of sulfate ions per mole of potassium sulfate that dissolves. So we get those concentrations for those constituent ions. All right, let's try another one. Take a look at number 9 on that same page. Again, we want to determine concentrations of the ions in each of those solutions. And I think I'll just have you do letter A. If you want additional practice, certainly do letters B and C as well. So I'll give you the answers to all of them, but definitely do letter A. Find the concentrations of the ions in that solution. This time we are given masses of solutes. Go ahead and pause the video and do that now, please. All right, so this time we need to take the mass of the solute and use that to find the concentration of the solution. So convert that to moles first, divide by the volume of the solution in liters. And so the solution as a whole, aluminum sulfate, concentration 0.00423 molar, and then apply your mole conversions to get the concentrations of aluminum and sulfate. Done the same thing for letters B and C. Now, something you should ask. Did you do B and C in addition to A? I didn't say that you had to, but are you struggling in this class? If you are, then you best be taking advantage of every opportunity you have for practice and definitely should do B and C. Are you doing great in this class? Well, if you are, then maybe you don't need to do B and C. But I'm guessing if you're doing great in this class, you probably did do all 3 of these. No coincidence there. All right, let's take a look at what's next. We have the auto ionization of water. That prefix auto means self. So water all by itself ionizes. It forms ions. So let's take a look at our equilibrium equation for the auto ionization of water. So think of it this way. One of the water molecules acts as a Bronsted-Lowry acid. The other acts as a Bronsted-Lowry base. So we have a proton being donated, a proton being accepted. And so we end up with these ions in solution. Now it should be noted that this is occurring in every aqueous solution. Very, very, very important. That means in every solution, there are hydronium ions, H3O+, and hydroxide ions. And something that we'll look at in just a bit is the relationship between the concentration of hydronium ions and hydroxide ions in solution. Now, any guesses where the equilibrium lies in this case? Is this reactants favored or products favored? Are there lots of ions in water or not a lot of ions? Let me write this another way too. We can write it with just one water molecule. And if we write it like that, then instead of H3O+, we just get H+. So either way for those are fine. All right, so let's do this. Let's take our equilibrium equation and from that derive our Kw expression. Kw is the ionization constant of water. It's the equilibrium constant for the auto ionization of water. So Kw equals, and I'm going to use this bottom equation. Again, either way is fine. We get concentration of H plus times concentration of OH minus over not over anything. Water is a liquid. So either H plus or H3O plus times OH minus. That gives us our equilibrium expression. Now take a look. What is the value of Kw at 25 degrees Celsius? Remember, K's value does vary with temperature. So at some other temperature than 25 degrees Celsius, Kw has some value other than 1.00 times 10 to the negative 14th. But at 25 degrees Celsius, which is where we will assume that the solution concentration is in almost all of our calculations, we're going to use that value for Kw. Now, what does that mean? Look at the value. Look at the magnitude of Kw. Does that mean the reactants favored or the products are favored? Well, K is really small, which means the reactants are favored, which means there are not a lot of ions, not a lot of H plus and OH minus ions in water. You got mostly water molecules. Next up, very, very, very important. So let's do this. Think of the H plus ion as the ion that makes a solution acidic. So if you have a lot of H plus ions, solution is an acid, it's acidic. Likewise, think of the OH minus ion as the ion that makes a solution basic. So you got lots of OH minus ions, then the solution is basic or is a base. So how about this then? What if the concentration of H plus and OH minus are the same? So what do we say? Well, that solution then is, you can say it one of two ways, neither acidic nor basic, or I like to think of it as equally acidic as basic. There are H plus ions in neutral solutions. There are OH minus ions in neutral solutions, but the solution is neutral because the concentration of them is the same. Now, what is the concentration of H plus and OH minus in any neutral solution at 25 degrees Celsius? Well, they're going to be the same. So if we go back to our equilibrium expression, we can plug in X for H plus and X for OH minus. So we get X squared, not 2X. X squared equals 1.00 times 10 to the negative 14th. Which means that the concentration of H plus and OH minus ions in any neutral solution at 25 degrees Celsius is 1.00 times 10 to the negative 7th molar. Let's think about Le Chatelier's principle and the above equation that we just wrote on the previous page. Suppose you add something that increases or adds H plus ions to solution. As a result, your solution then will have a greater concentration of H plus than OH minus. So if this is the case, anytime this is the case, the solution is acidic. Something is an acid if it has more H plus than OH minus. Conversely, if you add something that increases the concentration of OH minus, you're going to end up with a solution that has a greater concentration of OH minus than H plus. When that is the case, we say that the solution is basic. So make sure you know, truly know, what acidic, basic, and neutral means in terms of concentration of H plus and OH minus. Now it says the amount of the shift is usually negligible unless you're dealing with extremely dilute solutions. So here's the deal. The moles of H plus that are added, say, to water equals the moles of H plus in the solution. So if you add some hydrogen chloride gas to water, yeah, there's already H plus ions in the water, but it's a really low concentration, 1 times 10 to the negative 7th. So the significant amount of H plus in that solution comes from the HCl dissociating or ionizing. Likewise, moles of OH minus added equals moles of OH minus in the solution, again, because you're adding that to 1.00 times 10 to the negative 7th, which is really, really, really small. All right, take a look on 704 and 705. 18.2, read along. It says calculate the concentrations of H3O plus or H plus and OH minus in a 0.05 molar solution of HNO3. So let's start off with our balanced dissociation equation. So I'm going to add a slide here. So HNO3 in solution we call nitric acid. Nitric acid is one of these strong acids, so we want to write a one-way arrow here indicating that. And so what we need to do is apply what we said earlier. So this was 0.050 molar. And if the concentration of the solution as a whole is 0.050 molar, and we have 1-to-1 ratio of ions in solution, then their concentrations are also 0.050 molar. True or false? This solution, besides H plus and NO3 minus ions, contains hydroxide ions. Go ahead and answer that now. If you said true, then you are correct. I can't say it enough, I guess. All aqueous solutions contain both H plus and OH minus ions. Well, this is an acidic solution. This is an acid, so the concentration of H plus must be greater than the concentration of OH minus. So what is the concentration of OH minus in the solution? Well, that's when we're going to use, or that's why we're going to use this. We'll use Kw. So if we know the concentrations of one of these ions, either H plus or OH minus, we can find the concentration of the other using Kw. So let's go ahead and do that. So we're going to put concentration of OH minus equals Kw, no units, divided by concentration of our H plus ions. And even though that has units and Kw doesn't, we're going to get units for OH minus. Go ahead and pause the video, punch that up, and see what you get. All right, you should get, I think we want 2 sig figs here because of the H plus concentration. 2.0 times 10 to the negative 13th molar. Look at that. Concentration of H plus is way bigger than concentration of OH minus. Of course it is, because this solution is an acid. All right, so that's how we do that. Go ahead and do 7b on page 736. I already gave you the concentrations of the H plus and ClO3 minus ions. Go ahead and determine the concentration of the OH minus ions in that solution. Go ahead and pause the video and do that now. So there's our setup again. Kw divided by H plus equals OH minus. We get a really small concentration of OH minus. Again, this is a solution of a strong acid, so we'd expect a small concentration of OH minus. I think there's a typo in your notes, so go ahead and do 7a. Same thing. We've determined previously the concentration of Sr plus 2 and OH minus. Calculate the concentration of the H plus ions in that solution. Go ahead and pause now. Once again, we get a really small number here. Of course we do. Strontium hydroxide is a base. There's a lot more hydroxide ions in that solution than hydrogen ions. Something else to keep in mind. So let's say I gave you this. I'll just make up some random number. And I said, tell me if that solution is acidic, basic, or neutral. What would you do? Well, probably the easiest way is to compare that to 1 times 10 to the negative 7th. Why compare it to 1 times 10 to the negative 7th? Well, that's a concentration of either H plus or OH minus in a neutral solution. So this is less H plus than in a neutral solution, which means then that this solution must be basic. Likewise, what if I gave you a hydroxide ion concentration of this? Would that solution be classified as acidic, basic, or neutral? Well, this is greater than 1 times 10 to the negative 7th, so there's more hydroxide in this solution than there is in a neutral solution. So that tells us that this solution is, once again, basic. What if I said there's an easier way of determining if a solution is acidic, basic, or neutral? Be interested in learning about that? All right, well, that's our next section here. pH and pOH scale. Maybe you haven't heard about the pOH scale. So the P in pH, or the P in pOH, or the P in pKW, as we'll see in a little bit, technically means power, but I think of it as negative log. So what exactly is pH? pH is the negative log, not an H, negative log rather, of the hydrogen ion concentration. So what's pOH then? Well, must be something similar. pOH is the negative log of the hydroxide ion concentration. How about pKw? Well, same thing. pKw is simply the negative log of our ionization constant for water. Now, some of you asked about significant figures with logs. Technically, here are the rules for sig figs with logs. It says only the digit after the decimal in pH, pOH, pKw are significant figures. The number or numbers to the left of the decimal are derived from the power of 10, and they are not significant. So for example, let's say we have an H plus concentration of 1.00 times 10 to the negative 7th. What is the pH of this solution? So type it into your calculator. Take the negative log of 1.00 times 10 to the negative 7th, and we get a pH of 7.000. So notice in our concentration we have 3 sig figs, so we want 3 digits after the decimal. What if we had an H plus concentration of 3.6 times 10 to the negative 3rd? Again, that's H plus concentration. What would be the pH of the solution to the correct number of significant figures? Hopefully you got 2.44. We have 2 sig figs this time. In our concentration, we need 2 digits after the decimal. One more, 3.6 times 10 to the negative, let's go, I don't know, negative 2. What is the pH of that solution? Again, that's an H plus concentration. Notice that the only thing that's different is that's 1 versus 2.44. All right, turn to page 706. Example 18.3. Calculate the pH of a solution that has a H3O plus concentration of 0.050 molar. Again, very easy. Take the negative log of that, and we get to 1.30. Something I did not mention before, but hopefully you are familiar with the pH and pOH scale. So pH of 7, as long as we're at 25 degrees Celsius, is neutral. pH less than 7 is acidic. pH greater than 7 is basic. A lot of times we learn 0 to 14 is the range. That is not necessarily true. There are solutions that have pHs that are less than 0, solutions of like strong acids. There are solutions that can have a pH of greater than 14. So don't just limit yourself to 0 to 14. All right, it's your turn. Go ahead and do number 23 on page 736. And check in a bit for the answers. Pause now, please. All right, here's our results. Letter A, that's a strong acid, hydrobromic acid. So concentration of HBr is going to be equal to the concentration of H plus, 1-to-1 ratio there. Take the negative log of 6.5 times 10 to the negative 3rd, and you get 2.19. So we have 2 significant figures in our concentration. We need 2 digits after the decimal. Letter B, also strong acid, hydroiodic acid. So H plus is 0.0042 molar. Take the negative log of that, and we get 2.38. Letter C, we got to find concentration of that solution first, like we did earlier in this lesson. Concentration of HNO3 is 0.0931, I think. I can't really read my writing rather. And so that H plus concentration is also 0.0931. That's 3 significant figures, and so when we take the negative log of that, we want 3 digits after the decimal. All right, 18.4 on page 706. Take a look there. It says the pH of a solution is 3.301. What is the concentration of H3O plus? So we're going backwards. To go from pH to H plus concentration, we're going to take the anti-log, that's the 10 to the x, anti-log of the negative pH. So 10 to the negative pH. So our pH was 3.301. So we're going to go 10 to the negative 3.301. If you go anti-log of pH, you're going to get a really big number, and that doesn't make sense. So make sure to do anti-log of the negative pH, and we end up with 5.00 times 10 to the negative fourth. All right, very, very, very important. Letter H, since H plus concentration equals OH minus concentration in pure water or any neutral solution, that value being 1.00 times 10 to the negative seventh, that means the pH and pOH of pure water or any neutral solution must be 7.000, as I mentioned before. Now, useful relationship, let's derive something here. So let's go back to our KW. Whoops, I don't want equals, I want times. So concentration of H plus times concentration of OH minus equals KW. Let's take negative log of both sides. So negative log of H plus times OH minus equals negative log of our KW. And we get negative log of H plus, because we're multiplying, right? Negative log of OH minus equals negative log, negative log of our KW. Well, what's another name for negative log of H plus? I'm going to write that over here because I'm out of room. Negative log of H plus is called pH. What is another name for negative log of OH minus? That's POH. And not what is another name, but what is the value of the negative log of KW? That is 14.000. So the sum of the pH and POH for a solution, any solution, is 14.000. All right, I think we've gone on long enough. We'll do some more practice later. I think we'll save these for later, but you should have enough to be able to do your homework. All right, we'll continue next time with some more of these. Thanks for watching.